Hello, my name is Ashley Cetnar, and I'll be sharing on concept inventory development for medical physics education. I'm presenting this work on behalf of the ASTAMP Medical Physics Education Research Subcommittee. Physics is foundational knowledge for the field of radiation oncology, and the understanding and application of the principles of radiation interactions are essential for residents to be successful clinicians. Concept inventories are research-based multiple-choice tests used to evaluate basic concepts of students' thinking without the use of extensive problem solving. In this study, we developed the first concept inventory for medical physics. There are 6 core topics described as essential components of graduate study in medical physics. We developed a concept inventory in radiological physics and dosimetry. A working group of content matter experts was formed to create concept inventories for medical physics topics. Radiological physics and dosimetry was selected as a core topic for the assessment, and initial open-ended questions were developed by interviewing medical physics students and residents to better understand how learners approach fundamental concepts. After diligent evaluation of responses, 26 multiple-choice questions were developed with distractor options utilizing common misconceptions about physical principles. The assessment was reviewed by medical physicists and then piloted in a single medical physics graduate course for initial feedback. Data has been collected in a multi-institutional instrument validation study with pre- and post-test design, with data reported from 25 students. Classical test theory was used to assess the instrument for medical physics graduate students. Graduate program directors were contacted via email to notify directors of the study. The program directors provided approval for their graduate program to participate in the study with contact information for the course instructors. The course instructor was provided information about the study, and consent was required for the instructor and the students to participate. Demographics are shown from 3 institutions, and a total of 25 students completed the pre- and post-test. The graphs show that many of the students in the study include first-year students in PhD programs who are taught in person with an undergraduate physics major. The results from the post-test were analyzed using classical test theory. In this slide, we see the evaluation from the item score, or how many students that got the item correct. This can be converted into a difficulty index, which is the number of correct responses over the total number of students. The higher the number is, the easier the question is. Discrimination can be calculated by splitting the students in half by the top and bottom half of performers and investigating how well they performed on each item. This metric ranges from -1 to 1, where the closer the item is to 1, the better discrimination value it has for identifying the difference between the performers. We currently have several items that can be investigated because of the values lower than 0.2. The next metric is the point biserial index, and it's a correlation metric between the performance and the items. Using this metric, there are 4 items that are less than 0.2, which can be considered. The reliability of the test as a whole, or the internal consistency of the items in the current exam, was measured using the Cronbach's alpha with a reliability of 0.7, which is on the border of good and somewhat low. The average gain between the pre- and post-test is 13%, with normalized gain of 0.29. We are currently working on the refinement of the assessment and look forward to the implementation of the next version of the study for additional institutions in the fall. Thank you very much for the opportunity to present today on behalf of the team.